So now, what happens if we make a solution of two things that are both volatile? So for example, maybe something like alcohol and water. Alcohol definitely has a vapor pressure. Water definitely has a vapor pressure. Okay? So the calculation gets a little bit more complicated. So we have to now calculate the mole fraction of A and the mole fraction of B. We have to multiply those mole fractions by their respective pure vapor pressures, add them together, and now that's going to give us the vapor pressure of the new solution. Okay, so again, this version of Raoult's law applies to solutions made of two volatile components. So basically what that means is two liquids, if I mix two liquids together. Okay, so let's do a sample calculation. So a solution is made by mixing 45 mils of ethanol, so that's alcohol, with 123 mils of water at room temperature. Calculate the vapor pressure of the solution, assuming ethanol has a vapor pressure of 5.95 kPa, kilopascal, and water has a vapor pressure, so the same 17.5 torr. Okay? So the first thing to notice is that we have to have those pressure units the same. And it doesn't really matter if we convert to kilopascals or torr. They just both have to be the same. So I'm going to convert this 5.95 kilopascal into torr. Okay. So I recognize from my little chart here, right, that you always have these numbers on an exam. I'm not going to make you memorize them. 101.325 kilopascal is the same as 760 torr. So let's say 760 divided by 101.325 equals, and let's see here. Oh, and then I have to multiply by 5.95. And then times 5.95 equals. Okay, great. So that's 44.6 torr. Okay. So, and let's see here. What's also missing is I didn't give you the density of ethanol. So that I would definitely have to give you. So the density of ethanol is, I got 0.786 grams per milliliter. And we recognize the density of water is 1.00 grams per milliliter. Okay, so we'd have to have both densities of these liquids. So now, first I'm going to calculate the number of moles of ethanol, which I abbreviate as ETOH. Okay, and so that's going to be my 45 milliliters times now. So my density says, let's see here. 1 milliliter is 0.786 grams. And then now I gave you the formula. So you'll need to remember how to do molar mass, right? So the mass of 2 carbons plus the mass of 356 oxygens hydrogen, plus the mass of an oxygen. I get 48.07. Make sure you get something close to that. 48.07 grams in 1 mole. Okay, beautiful. So when I do that, now I've got here 45 milliliters times 0.786 divided by 48.07 equals 0.736, let's say. So 0.736 mole. I'm going to go 1 digit past my number of significant digits, and then I'll estimate my sig figs at the end. Okay. So then now I got to figure out my moles of water, which I can do the exact same way. So 123 milliliters of water. So I know the density of water is 1 milliliter in 1.00 grams, and my molar mass of water is 18.01 grams in 1 mole. 123 mils times 1 times 1, and then divided by 18.01. Hopefully I did that correctly. Yep. So now that's 6.83 moles of water. And so now I can say my mole fraction of ethanol is going to be the number of moles of ethanol divided by the number of moles of water plus the number of moles of ethanol. So I'll write that out. I'll say N ETOH divided by N ETOH plus NH2O. And so that's going to be 0.736 mole divided by 0.736 mole plus 6.83 mole. Okay. So I'm going to leave this number in the calculator, and I'm going to say plus 0.736. I'm going to do this handy 1 over x trick, and then say times 0.736 equals. And let's see, for my ethanol, that looks right. I get a mole fraction of 0.0973. Okay. And now there's a couple things I could do. I could calculate the mole fraction of water in the same way, or I could recognize the mole fractions have to add up to 1, right? So let's calculate it in the same way that we did for ethanol, and I'll know that I did it correctly if both of those mole fractions add up to 1, okay? So that's going to be the number of moles of water divided by the number of moles of water plus the number of moles of ethanol, which is going to be 6.83 moles divided by the same thing, 0.736 plus 6.83. Okay, so let's see what we get. So I'm going to say 0.736 plus 6.83 equals 1 over x times 6.83 equals, and here we go. I get 0.903. So I think we did this correctly, because now if I say plus 0.0973 equals 1.000. Great. Okay. So if you want to make a shortcut on calculating mole fraction, where you have to calculate both, you now know you only have to calculate one and then subtract that number from 1.000. Okay. And so now finally I can say the vapor pressure of the solution equals, it's going to be, so mole fraction of ethanol is 0.0973 times its vapor pressure, which was 44.6 torr, plus the mole fraction of water, 0.903 times its vapor pressure, 17.5 torr. And let's see what we get here. So that's going to be 0.0973 times 44.6. Okay. So that's going to be 4.34 torr plus 0.903 times 17.5 equals, and that's 15.8 torr. Okay, so adding these together, plus 4.34 equals, and I get, with the correct sig figs, that's going to be 20.1 torr. So there was a fairly significant change to the vapor pressure of water with this ethanol solution. The vapor pressure increased. And that's because ethanol has a much higher vapor pressure than does water. Okay? So all of this stuff that we've done are what we call colligative properties. Okay? So, and what colligative property means is it's a property that depends on the collection. And no, I'm not talking about the Borg. I'm not going to assimilate you. So this collection, it really means like the number of things in solution. Okay? The more things that we have in solution, the more significant are these colligative properties. So examples of colligative properties, vapor pressure lowering, like we just talked about. And the other two important ones that we'll talk about, boiling point elevation, freezing point depression, and then the last thing that I forgot to include on this list, osmosis. Okay, so osmosis is definitely dependent on how many things are dissolved in solution. Okay, and so I'm going to end it here, and I'm going to pick up right here for the next lecture, so we can have kind of two final lectures here, about 30 minutes each. Okay, folks, I'll see you in the next one.